Should we start? Are we waiting? What? No, not waiting. No.
Shall we start?
Yeah.
Okay, so today I'm going to talk about the paper from
You're going to be talking very far away from the microphone.
Yeah.
I think this will be a problem.
That's right. That's right. Thank you.
Okay.
Yeah. Holding your hand is constant distance.
Okay.
Yeah, that's good.
So this is a scalable distributed deep reinforcement learning with importance weighted actor-learner architectures. And this is the main training technique used in the AlphaStar posted recent. No, the blog is posted recently by the DeepMind, and so I want to introduce I want to introduce this paper, and I hope it will help you to understand that AlphaStar in the future.
AlphaStar, did you say?
Yeah, AlphaStar. AlphaStar used in panel as a training technique. It's
AlphaStar?
it is AlphaStar plays the StarCraft game. It is a very complicated game. And this is basically a actor-critic algorithm and with distributed settings. And it is an off-policy actor-critic. First of all, I want to
This way. Okay. What point this way?
no, it's not working. So first of all, I want to introduce why in panel is it is not only off-policy actor critic. It is designed for multitask learning. I want to introduce why we care about this multitask environment. Because for single task learning, we can already there are many algorithms that can do very well on single task learning. So we want to find a general agents that are able to do many tasks simultaneously with one network. And going from one network per task to one network for tons of tasks has many challenges, including the data efficiency. Because for a single task, we need hundreds of millions of frames to train. And if we, for example, if we want to train 30 tasks together, we may the frames we need will be 30 times of the single task. Of the single task. And if we want to train 30 tasks together, we may use 30 times and 30 times the frames we need for training a single task. Just means I'll need a lot of data to train multitasks. And
I mean, that you're stating a fact, or you say this is an alternative way of either less data or what?
but this is a fact. I mean, if, for example, if we train a single task, we need 1 day to train a single task, and we might need a month to train 30 tasks.
That's obvious, right? That's
Yeah,
obvious.
yeah.
30 times more data, right? That's not news.
Yeah, but I'm talking about the challenges if we want to train multitask.
Okay.
Okay, so the first challenge is data efficiency, and the next challenge is stability. It means do we need? It means for each. It is about hyperparameters because for each task, the best hyperparameter may be different. And if we want to, if we want to merge it in one network, then maybe we need we need a general hyperparameter. The network structure and even the learning rate should be the same. And another challenge is the scale. It means that we may need a more complicated architecture, and the training process might be slow. The last challenge task interference means multiple tasks may cause interference with each other, or they may help each other. We don't know if they interference with each other or help each other before we search into the problem. And next, we want to do a short review of the DQN and policy gradient and actor critic algorithms. In reinforcement learning environment, and the basic setting is that there's an agent interacting with the environment, and at each time t, agent takes an action A, and the environment returns the agent with a reward at t+1 and the next state as t+1. And our goal is to maximize the total future reward, but the discounted total future reward. And for the policy type, the action value function Q is just the expected total, discounted total future reward, expressed by this formula. And Q. Oh, sorry. This is the next. This is of this is plus. Yeah. And Q represents how good an action A is given state S. And the optimal value function is the optimal value function gives the maximal achievable value Q star. And given an optimal value function, we can get an optimal policy. We could just choose the max of the action value, and both the optimal value, both the action value function and the optimal value functions obey a Bellman equation. And deep Q learning is to the basic idea is to make Q learning look like supervised learning. So first of all, we connect a batch of data from past experiences, and we use techniques such as experience replay, and we use data previously. It can achieve better data efficiency, and it makes the data distribution more stationary. So at each time we choose a batch of past experiences from the replay buffer, and then we do a mini batch SVD on the data to learn the temporal difference L2 loss of the action value function. And there's one, and in the deep Q learning setting, we use an older set of ways to compute the targets network. It is to keep the target function from changing too quickly.
Before you moving away.
Okay.
On your third third one, third bullet point there. Okay, so the inside inner circle, makes the data more stationary, right? You didn't use independence, right? You talk about stationarity.
Yeah.
So if you sample from nuclear buffer, which means that this data point is from maybe much past. The next data point is they are not mini batch. They are really scattered around time horizon, right? At different time points.
Yeah.
Right. So is it really emphasis on stationarity or the independence? Right. Sometimes you want something sample IRD. I think this gap memory buffer are enough that maybe that's very independent. For the Markov chain, if you sample the next stage, that's going to be from the previous stage. That's obviously not independent, right? Also, it's stationary, okay? Stationary for something, but they are not independent. But if they are, the gap of the window, time window, far enough, then they become more like independent. Right? Now, there's also issues. That's one issue. Another issue is that I try to make this replay buffer may be from different policies, right? It's not just it's not previously just a current policy or something, right?
Yeah.
It could be that a memory that the server policy.
Yeah.
When policy changes, they adopt stationarity to code. Probably not. Right? You are completely data points generated from different scenarios, different situations. But anyway, this is a minor point. I just want to challenge this thing.
Okay.
Do you understand my point?
Yes, I understand that. I didn't quite understand, but I understand that.
You didn't quite understand the last part? I mean, is this right? The data, the replay buffer is experienced from server previous policy, server previous thing, right?
Yes.
And there's no evidence that the later policy and the early policy are there. So the data generated there stationary, it's not. Right? Maybe the one policy is going from east to west, right? Something.
Yeah,
another policy forces you from east to west, right?
Yeah, but actually, I think this focus on the data distribution. The replay buffer is very large, so every time, even if I add a small batch size of different policy, most of the data did not change. It's a very
okay. You're seeing that each new policy adding just a few data points to the data buffer, right?
Yeah.
However, I will challenge you on that. The AlphaGo 0 is actually this policy contribute half of it. You just use two. The old one just history just one policy. One policy with one policy. So each of them contribute half of it. Okay. Move on. I think this is something that just on the side, but I think we needed to.
Okay. So the deep Q learning network is very it is not data efficient. It is very not data efficient. So we have an alternative method called policy gradient. That means we could optimize, or we could directly optimize the expected return of a policy. So I think we introduced policy gradient just before, so I'll just skip it very quickly. And for different policies, the gradient of the policy gradient is just the expectation of the gradient of the log policy probability multiplied by the action value function corresponding to the policy. And the expectations is taking over states and actions. And this is an on-policy algorithm, means that every time we can only update we could only update the policy we use for the policy we use for connect data and the policy we are updating should be the same. For the queue, for the action, in the policy gradient, we cannot calculate the action value function directly, so we could use a simple sampling based method to calculate the action value function. That means we could simply draw out for several epochs and connect the expected rewards for the next few iterations, and this is called reinforce.
Which just to be clarified, the estimate Q, which policy?
The current policy.
Another approximation network going on?
This is just policy gradient. So
okay, so using whatever the policy, the current state of policy.
The current policy
to be valid in the Q.
Yeah.
Okay.
So
now I'm curious about your statement. So you said that your operating word is the previous slide Q learning is not efficient, right? You said something. First, policy iteration, policy gradient is more efficient, right? That's the motivation, right? Can you say something not efficient in what sense, right? I just give you this server things, right? Maybe sample not efficient. That's more, need more sample. When the computational time more, right? So the thing could be you navigate the accuracy you want. If you don't have the answer, that's fine. I just want to get something each of us to think about walking with them with this question, right?
Yeah, I thought it is not data efficient.
I think it's all related. I think the most important thing is maybe even more difficult. When computation time, when you never get to the accuracy you want.
Yeah.
Exactly.
Q learning is an off policy math.
Policy gradient is faster.
Yes, it directly gratifies the policy.
So, okay, so I want to think everybody so in the future presentation to better think about this issue, right? Not just using the operate word, more efficient, more something. What is, right? What is it? You need to help us, teach us to understand this more sharp. Okay. So,
and so this is the next page is to talk about how we estimate the Q value function. In the last page we talked about we could sample the action value function, and we could also combine it with the Q learning framework and update the Q value action value function by temporal difference and by the Bell equation, and we combine the policy gradient and the value estimation, and we get actually we get the actor critic algorithm.
Before you go on the previous slide, I think I structured. Do you hear that you have to assume the tabular representation of the Q, or there's actually network low dimensional representation is also similar? Is this the tabular representation of Q? Has to be.
This is not necessarily a tabular.
So if it's a low dimensional representation Q, neural network representation will be updated parameter.
No. You mean this update? This update?
Yes, it's update.
Yeah, this update. This is Q, right? I mean, tabular representation.
So this is the Q. This is the vocabulary representation. That's right for the most problem cannot. Right? It cannot update all the state.
But the deep learning. This is the deep Q network update.
Yeah, so this is why maybe say the action space is not large, right?
Yeah.
That has to be very small problem, which most of the interesting problems are action space.
Yeah. So. So for the actor critic, the agent learns the policy and the state value function together. And the loss function, it uses n-step returns instead of the one-step return. Instead of the one-step return, it means it roll out for n steps afterwards and use the we roll out n steps and use the n steps value function plus the previous discounted reward to add them together to estimate the action value function Q. And then we subtract it by the state value function to make the variance smaller. And and the policy the policy update is according to the first equation, and the value function update is trained by n-step TD learning. That is by minimizing the mean square error between the estimated Q and the state value function, between the estimated value function and the between the estimated value function between the target value function and the estimated value function. Yeah.
So you messed up some parentheses.
Is to determine theta, right?
It is to train the
minimization theta, right? Last one.
Yeah, minimize theta.
So the theta bar is the theta minus, right? The previous current.
Yeah, the previous parameter.
Yeah. So and theta minus is used in the maybe the previous waveform, right?
Yeah.
For B.
Yeah.
Okay. So here is you simulate one sample, one scenario, one episode.
Yeah.
One episode of length of n, capital N, right? Then you do that.
This is just actor critic, and for asynchronous actor critic, A3C. which equation? This one. And this one, this sorry, this should be here.
Okay. For this one, it's easier to look at the previous one. It's the gradient of the
Yeah.
policy.
Yeah.
The gradient in the previous slide. Go back to the previous slide. Yeah, that's right. The middle.
This is the same with this one.
Right? So the gradient is replacing Q with the related value function, right? Is the right Q related to the value function? Yes, Q using the one step plus the future, right? The value. But she's also taking out the constant.
Yes.
Which is independent of A, right?
Yes. So this part is an estimation of the previous Q. And this term is just a constant.
Independent of A.
Yeah. What? This is must be. I mean. Yeah.
So we can also use some.
Yeah, we could use any method to estimate the Q.
Bottom line is doing multi-step, not one step. Right? So is that next slide? Yeah, multi-step, and then try to do that of the estimating the Q, right?
So this is this is not generalized advantage estimate. Yes.
Not generalized what?
This is just M step. Just
yeah, TDM step.
And she mentioned that it's more like.
This means this is not. Yeah, this is not exactly GAE. It just means the.
Remember GAE is.
Yeah, GAE is different. It uses several numbers. They combine them together. Yeah.
Okay, so that's a separate model, right? So this is clear that you change multiple step A is a hyperparameter, right?
Yeah.
And once you change A into geometric random variable, then that's going to be connected to TD lambda, some version of TD lambda, right? Yeah. So when A is changed to the geometric random variable, okay, with some parameter lambda, then that's going to be some version becomes some version of TD lambda. Okay, that's something Mark talked about in the second lecture, right? Yeah. So that's a separate module. I think conceptually, I would like this one, not confuse with other things. This at high level, that's what we're doing here. That's something. TD lambda is exactly doing some version. Okay.
Yeah.
So so here is to right when n capital N is equal to infinite, the noise is too much noise there, right? And that's why you use Bellman equation. You reduce the noise.
Yeah.
But on the other hand, it's the bias. Yeah.
Okay. So this picture is an illustration of how the A3C does. It means we have multiple agents to generate trajectories together, and we connect the data. I mean, for each agent, we generate a sequence of experiences, and then we use the experiences to calculate a gradient, and we combine the gradients together to update the parameter. To update the parameters.
So
change it to that same parameter when they do this experience. Do they generate experience from same policy or not?
Yes, the same policy, because this should be unpolicy learning.
Okay. So all the agents accept the same set of marks they have, right? Same policy.
Yeah.
Right?
Yes.
And each of them generate a subset of experiences.
Yes.
And
So can you explain, is this a one task still or multitask already? Or-
This is just one task. This is just typical A3C algorithm.
Okay, so we haven't talked about multitask yet. Okay.
This is for one task.
Okay.
one task, just to multi-use, you make use of multiple processes available in the product.
Yeah, yeah.
So you're basically generating multiple trajectories.
You use multiple agents to generate multiple trajectories.
Okay.
Uh,
And average them somehow asynchronously, the updates.
Synchronous, yeah. And
You mentioned the synchronous, so means that update the weights of the neural network.
it just for each agent we have to wait for the agent to come here and then wait for all agents to finish before I start the next.
That's nice.
But the gradient calculation is separated.
But a gradient, how much data to that? They need many batches, right? Each agent needs many batches. So where do they draw many batches? That some older replay buffer is a common to everybody, or does each agent have different replay buffer?
Do they have replay buffer?
How do you do gradient? Do you need many batches?
Yes.
Where do you get it then?
Just connect one trajectory.
Right? Just using one trajectory. Because they don't use replay buffer. That's just observed on this episode. Each one that generates 3 episodes, say for example.
I'm not sure if a few episodes is okay, but actually it have to be unpolicy. It have to be generated by the current policy.
I see. So
What is graph they batch all scripts in one script?
you think they have common, they share the replay buffer?
Yes.
Yes, according to this graph, it seems like this.
By the way, I think I'm open to the idea somebody come back to discuss same paper to address the question.
I think
right?
I think in A2C it did use the same replay buffer, but in A3C maybe not.
If we want to increase each agent should have its own.
Yeah, I think so.
And they update the weights.
Mm-hmm.
Otherwise, it is.
Yeah.
I think it's a more powerful one, but I agree with you. That's truly the word. If you want to use that word, I think then it's really that each agent should be, I don't care about others. Everything just generated myself, right? What my information, something I find out you created. That's my creative update, right?
Yes.
Then you do the central scheduler, whatever you want to do, all this right update on the each agent.
Yeah, so just each agent calculated the gradient separately. And then for just for A2C, we connect the clearances together in a batch, and for A3C, we just separately update, separately calculate the gradient of each agent. And I don't have a good picture to illustrate that, but it is the A3C does not scale very well, because if we add actors, even if we add more, we could add more actors, and we could also add more learners, but we cannot. But we always have to But each agent have to start with the same policy, so we always have to wait for so it means that even if we could do asynchronously, we will have to wait for the total parameter to update before we start the next generating process.
Is that the term you use the multiple adding more actor model? The current way is just one actor?
Actor means the agents.
Agents.
Yeah, and learner means the gradients calculation agent. Actor means the actor to move forward. It means the agent to interact with the environment. And the learner means the agent to calculate the gradients.
Well, okay, I see. So I thought it was the actor becoming the policy, and the agent will carry out the policy, validate the policy. That's my original understanding. No, it's not same, right? It's not same. The actor, if so far here is only one actor determines the policy, right? And that every agent uses same policy. You know, scenario will be different. But
the actor here just means the agent to interact with the environment.
okay, fine.
And
why communicating gradient is bad?
This just means that it means that we have to communicate the gradients calculated by each agent together to combine them in a total update, and it just means that we have to
synchronization with slow down everything or whatever it is, right?
Yeah. So we have a better architecture to centralize learner and distribute the active. It means that actors only this actor here just means the agents. These actors receive parameters and send only observation to the learner. And this is just each actor generates a batch of trajectories and connect them in a larger batch, and the learner pick up the learner just pick up a mini batch. Every time the learner pick up a mini batch from the large batch and calculates the gradient. And for every time an actor wants to start to roll out, it pick parameters from the learner at the time at the current time. It means each actor could start at different parameters. And actually, this is just off policy. And
it's not very clear. Can you say that or that again?
Because the actors only receive parameters and generate trajectories.
It doesn't do any local updating. It doesn't calculate the gradient.
Yeah, it doesn't calculate the gradient because it doesn't calculate the gradient.
It sends the observation instead, and then let the learner calculate the gradients together after receiving multiple observations from different actors.
Yeah, it doesn't have to wait at all. It means that the observations are stored in a replay buffer, just as in DQN. It can store the observations in a replay buffer, and the learner choose from the replay buffer every time. It doesn't have to wait for the actor, or actors doesn't have to wait for each other. Nobody has to wait.
So let me replay this. Okay, so this is a centralized replay buffer, accessible by every agent. Well, every agent contributes to that
Buffer.
replay buffer, right? There's one central pool of replay buffer, right?
Yes.
So scheduler, learner, there's only one learner, right? The one learner is draw whenever draw many batch from the central one location, one memory, one display power, right?
Yeah.
And but every time the learners keep doing update, right? Updating the gradient.
Yeah.
So each learner has something. So assume the communication there's no delay. Something the agent is able to put out. I want to generate data point. I'm not sure to generate a.
今天是2月25日。
What's going on? Okay.
So the learner is doing the gradient update.
Yeah.
Learner access to the global information currently, global information through this memory.
Yeah.
And learner update that and put it into central location for the memory buffer or whatever something that every agent can access.
Yeah.
Now the learner is now the question each agent update generate once the graph the current parameter generate one data point or episode or something. That's another issue, right?
Yeah, yeah.
Okay. So I think okay.
So we could also use multiple actors and multiple learners. That's always okay. So this
but
is.
Before you go, I want to understand computer architecture. So that's kind of like a mini GPU. They can easily access to the same hard disk or same memory location. Am I right? That's something that the memory that a liquid buffer can be put into one location, but all the GPU can access to that. Yes. Okay. So that's okay.
So I think you mentioned the sequence that makes the actor contribute the observations and the learner update the places. I mean,
the agent actor contributes the observation. Yes. Asynchronously, right?
Yes, that makes the buffer is kind of decides this kind of multiple input. This time and rifle buffer.
Okay. Okay. So I think at this level, we just need to say it's essential for it, right? It's essential buffer.
Yeah, the next picture is a more clear illustration of how the process is going on.
Okay.
This is batch A to C batch A. This is just we always have to wait for the backward pass, and for this algorithm we connect data independently with the learning process, and so we don't have to wait. A to C is actor critic.
So it's not the sequence. The sequence.
Yeah.
So the persons previously talked about these things, A to C, A3C, the both are somewhere synchronized, right?
Yeah, they always have to wait because this is online.
So the on the right side figure is whatever that app name is. That's trying to say that's the new one we're talking.
Yeah.
The new one.
But the problem is we have to do off policy.
What did you say about GPU?
This is the caption.
Oh yes. Okay. Synchronization of code going on.
Yeah.
Yep.
So the key challenge of this operation of this algorithm is that it requires off-policy learning, and the actor parameters can lag by several updates. It just means it requires off-policy learning, and so the technique we use to try to solve the problem, to try to solve the challenge is that we use important sampling. And the off policy advantage actor critic is called V-trace. And the main update, the V-trace estimate for the value function V is the first equation, and the rho t here is it's just like importance. The rho t and ci here are all important sampling weights, but it is upper bounded by the constant to prevent it from blow up. This is just important sampling. This is this one. Yeah, we could notice that if we, if we consider only the on-policy case, it means that the mu means the policy we use to generate the data, the data policy, and the pi is the policy we are estimating. So if in the on-policy case this term is just 1, and if rho and bar and ci is larger than 1, then rho t and ci equals to 1. Okay, so if this all equals to 1, this equation reduces to the actor critic update previously.
Sorry, a stupid question maybe. What is on policy? What is off policy? What is that?
Yeah, on policy means that the policy we use to generate the data is the same with the policy we are estimating. I mean, it just means mu equals to pi in this. Yeah.
I see.
So let me just help a bit here. So we are in the policy gradient set, right?
Yeah.
Actor critic setting.
So you have a given current policy. We want to estimate its value function, right?
Yes.
Value function is used in the part of gradient update, right? Gradient update is that.
Yeah.
So the question is, how do you value the value function, right? The value function should be using the current policy, right?
Yeah.
Okay. So now this liquid buffer is now the policy is changing. The central player doing something, so lots of data put into the liquid buffer, particular agent.
Yeah.
And by that time, who knows which policy the data is from which policy, right? No idea. Now actually this is challenging to you. So who's updating this? This is like a Lana doing this, right?
Yes. Yes.
So Lana is doing this, but there's multiple mu coming on, right? There's something
the mu is recorded when in the data. When the actor samples trajectory, it just saves the mu information.
Not just data point, but also tell me what's key.
Yeah. It just means the mu is stored in the trajectory.
So mu is stored there.
Yeah.
In their point.
Yeah.
And pi is something currently from central scheduler point of view. That's something older. Pi is older data, right? Older policy. Something that at some point maybe is a checkpoint. Something that what's pi now?
Pi is the same with the pi in policy gradient. It's the policy parameter policy to be updated.
It's an outer loop. There's an outer loop somewhere, but this agent is doing some inner loop. They are aggressively grab the next parameter, right? The next parameter, the new keep updating, right, for them. But from out loop, the scheduler has to maintain more stable, slowly changing policy, right? I mean, scheduler, we haven't talked about the way the scheduler will update policy, right? Scheduler will be at some point will declare, this is the global, this is my new policy, right? So that's a pi, perhaps, right? Yeah. The pi is slowly evolving at a much slow scale.
Yeah.
Okay.
So this is just a weighted version of the previously actor-critic algorithm.
So maybe ask Professor Lu, is this
Okay, so let me try to understand this more. So these mu are locally stored at each actor?
Yeah.
Okay. So it has its current understanding of what the policy is. And it uses different, so each actor will have its own different mu.
right?
Right.
Okay. And uses different mu to generate the trajectory.
Not just each actor have different mu. Each data point is from different mu.
Right. So you use different mu because mu is changing, right? So it's generating trajectory using different mu and at different time. And spatially and temporally, they're all different, right? These.
Sorry, so I think each actor, if it generates one trajectory, they use the same.
Not necessarily, depending batch version or one sample version.
Yeah.
Right? I think there could be many multiple versions. Could it be just I generate 1 point each actor, each agent generate 1 point? I go to the central pool. What's your updated parameter theta, right? Parameter I'm using the graph.
Yeah, then you have a different mu. Then you use that to generate the next move, right?
Yeah.
Next epoch.
Could be the different version. One is to generate batch, right? They need you want grab one theta parameter, the generate batch of data.
In this formula, how many value network value function we
How many?
One.
What is?
One.
Just one value function.
We use the data which is generated from the point of view to update our value.
Yeah, the value function V is for part.
But the data is generated.
Yeah, that's the challenge. That's what the chief talking about. The data. The policy the V is the little part. Okay, the little part, but the data generated from this view keep changing. Yeah.
So basically, in the Greenfield paper, each time they generated n step.
They generate any step. Yeah, could it be any step or could it be in types? Could be something.
Could be
something. Yeah. Yeah.
So and they use the mean here. I think in their appendix they use it to prove some contraction.
Yes.
For why they use this because the original important sampling doesn't depend on your artificial robot and I think they use it to.
The Zoba and Seba is just used to limit it because this could be very large.
Yes, and because when you use important sampling, you will have variance because these higher mu can be very different, and they use it to eliminate some trajectory that is far away from the behavior part. I mean, behavior part is mu, current part is they are very different. They use this things to eliminate the.
And
well, I like this one so far. I like it because this one is purely can be model free, right?
Yeah.
The pi and the mu is from the neural network.
Yeah,
right?
yeah.
So that's okay.
Yeah.
That's our model. But in terms of underlying dynamics, we don't need any model. Right?
Yes.
Just experience, just observe experience.
Yes.
Good.
So the V-trace update for the value function is just to use the to find the theta to approximate the estimated V, and the V-trace update for the this is because it is based on the policy gradient, so we have value function update and policy update, and the policy update is just like it's just as in the in the policy gradient.
Good. I think this, at a high level, we understand what they or you try to do, right?
Yeah.
So we don't need to chasing down, I guess, or something. I think that now, I want to hear a story. We are close to 1 hour mark now. So what, right? I mean, I'm seeing that's something.
So I'll just go over this quickly. So this, I'll talk about the two theorems very quickly. The first theorem says that explains that what is the value estimation converges to. It says that it converges to the value function corresponding to this policy. And let's see, what is this policy? This term is just a normalization term. We could ignore it. So the policy is just to the minimum between the mu policy and the pi policy, or the weighted mu policy and the pi policy. And this is just I think I don't have time to talk about it very clearly, but it is just by multiply rho t by mu because the expectation is taken over mu. So we have here a term mu multiply by rho t, and this just get this term, and normalize this term, we get this policy. Yeah, but it's in the proof actually. So the value function would converges to the value function corresponding to this policy.
Okay, so slow down here. So we are assuming pi never changes, right? At this point. Convergence under the assumption pi never changes, right?
Yes.
Okay, so pi never changes, just at least at time scale that the pi changes very slowly, right? So it never changes. So what's going to be changing is this mu to keep updating changing, right?
Yes.
So there's a lots of mu changes. Eventually, if let's frozen pi, then what you claim is that this process will converge.
Yeah, the Waitress operator, the value estimation, in the previous slide, this value estimation would converge to the value function of a policy named pi rho bar.
Pi rho bar.
Yeah.
Okay. And suppose presumably that's the next. That's for the scheduler to update policy should be updated to this policy, right? Can scheduler start with current policy, right? Scheduler at some point we update this policy. Update to new pi, right?
Yeah.
The new pi will be this policy, right? Eventually.
Approximately.
Approximately. Then after that, all the agents using different mu.
Yeah. If rho bar equals to goes to infinity, this just equals to pi. It just so, and if rho bar is 0, then it just equals to.
That's your point.
Yeah.
That's your point. So rho bar, this pi bar in 4 if rho bar is big enough, that will be equal to pi.
Yeah. So this pi is between mu and pi.
So this provides some consistency that the mu, the value function value is almost the value function for pi.
And the next argument is to say that the Waitress operator is a contraction mapping. So we get the second theorem to say it just say that eta is less than it's the Waitress operator estimation operator is eta contraction mapping, and the eta is less than 1. This is to prove the convergence for in the theorem 2.
So the bottom line that first display the operator is contraction map.
Yeah.
It's contraction operator.
Yeah.
Right?
Yeah.
Okay.
So
and because the contraction operator then is stochastic. This is basically stochastic approximation average, something right?
Yeah.
The value function stochastic is a stochastic gradient, stochastic approximation average resolving the fixed point equation. Right?
Yeah.
Okay.
Yeah. So the theorem 2 is a direct derivative of the previous theorem. It just says that Vk converges to V pi. This is just the learning rate condition.
Assumption
So this doesn't care that the sample, batch sample mu is each mu is the agent, just sample 1 point. That's okay. A few of them, that's okay, right?
They are all okay, I think. But
So basically, they define the new operator you set up with similar to the
yeah,
analogy.
yeah, it's all similar.
It's very similar to even clear, I mean, earlier on physical.
On
Right?
what?
Beyond physical, these are stochastic, right? The stochastic approximation algorithm is all very fun, right?
I would mention this algorithm.
This algorithm used.
Yeah, I mentioned it before.
Most recent.
The DeepMind has a recent breakthrough with AlphaStar, and for that, is that game more challenging than Go?
Yeah, much more challenging.
What's that game? It's a computer game?
Yes,
Or game?
it's has far more action space, and it's a big imperfect game.
The state knowledge is imperfect.
Yeah.
Unlike AlphaGo, everything is completely rules directly.
And the space is
Space I can understand. Actually, action space. So AlphaGo 0 is not that action space, is not that big, right?
Yeah.
There's also some multi-agent based
Yeah.
collaboration.
Yeah.
There's a game, computer game.
Oh, so
Okay, so that's this algorithm.
one of the algorithms they use is this.
One component.
Yeah,
Of
one
that
component.
component.
The main training component.
Actually, this paper is also.
Yeah.
Okay. That's
So-
that's interesting. I think that's right. Right.
So I want to show the results.
Yeah, sure,
I haven't talked about the multitask.
You haven't talked about.
I haven't talked about the multitask settings before.
But we can schedule another talk. If you want. I think I suggest.
I agree. I think we should schedule another time because I have to
Paper.
stop here.
Okay. But,
Yeah.
uh,
I think let's put the multi-agent one. Should we schedule another talk?
Or leave the unfinished part to the next time and then we continue there because I have to leave now.
Yes, he has to leave. I think it's we should think about that. For you to you make a trip right here. Are you still existing Tencent now?
yeah, but from Tencent to here, also far, yeah.
Far away. I think we should schedule another talk. I think we talk about that.
Oh, okay.
Yeah.
There's no point to rush things. It's more important to learn things better and well.
You don't need to just finish the task.
Yeah.
For us to then have an extensive discussion with everybody benefit. So do you have something comparison? Is this for the single agent or multitask?
This is for the multitask environment, and the next page is the multitask performance. It is apparently better than the A3C.
I think I haven't really heard about multitasking yet. We should talk about that another time. And I also need to go. So do you have something that numerical work for what you currently talk about? Nothing, right? Nothing, no numerical work for the one you currently talk about. Single task one, there's no numerical work.
What? Sorry.
Any plot, any graph for single task.
This is for single task. Yeah. This is for single task performance, and then this is for single task stability. It means both the performance
Okay,
and the.
let's slowly talk about finishing this slide.
Okay.
Then we call.
Okay.
Right. I suggest that then we schedule another talk for you.
Okay. Fine. So, on the top row, is the is the mean return of
So what is the problem? And you think about that.
The problem is just some of the tasks means choose one of the just rooms or water maze, like water maze, castles, opponent. Those it's just
So
just
different single task games.
yes,
something like
different
that.
single task games,
Yes,
and
right.
we choose 5 single task games to plot, and in each plot we plot the impeller algorithm compared with the blue line is the impeller and the red line is the A3C.
Okay, so now let's see. Pick one something. But I can't see. I don't really use it, but that's what
The x-axis is the environment frames. It means how many frames we have put into the network. And
what's that? I don't understand that.
frames, just like how many steps we, how many frame means the picture, how many frames of pictures we put into the network altogether. And this is the x-axis.
I think that means
In the data we.
So when you're doing computer game, you basically directly ask of the how people see this game. The frame is one picture.
How much you allow the player to see this? Is that right?
It's
with the
how
game
long we play. It means if we, for example, AlphaStar, we 200 years of games. I mean, how long of data we put into the network together
As I
to train.
understand, the time is continuous in the game. So each frame, 1 second, or each frame, 0.1 seconds, we take a picture or take a frame of the current situation in the game.
Basically,
It's
basically it's the state.
Take the current state.
The current state game is not current snapshot.
It's a current snapshot. So each like 1 second, we take a snapshot.
Yeah.
Of the game.
Yeah.
And this is like a frame.
One snapshot is has many frames or one frame? One frame. So this meaning that how many snapshots, how long frame? This is really length of game.
Yeah, length of games we experience.
Still by
Right, I understand. So that's basically length of a very long frame.
Yes.
Yeah.
Now the length of the game can continue to move on. Continue
Yeah,
beyond, okay?
yeah.
There's only one action.
It's not, I think it's not limited. Frames just is the concept in videos as frames per second.
It has something to do with what the players do, like this.
Yeah, so you can frame, then you pick the next. You will pick the section.
and you see the next.
It just means how many data points are there altogether in our.
So the one frame can be the pinpoint to one thing. One frame is something, the snapshot, maybe I think might understand the screenshot. And then the player decide what to do something. Then next second or next something, the screenshot will change.
So in each screenshot, the player can choose something.
After taking screenshot, the player can do nothing or do something. Yes.
Yeah,
I think
and
that's
between frames, you keep doing the second. You basically
Because you estimate the states from the image, and then you put it in your network, and output your action. Then the environment interact with the game, and then you see the next frame. This
So all you see is the result of the player's actions.
what do people see it.
You don't know what the action was taken, you just see the results.
You
How
just
with essential scheduler, they neural network do they see can they record the decision of action?
That's in the buffer.
There should be, yeah.
That's in the replay buffer.
That should be information relevant. Okay, so now let's see this one here. So this player return meaning there's scoring going on. Something I think the video game is score.
Yeah, returns some kind of score.
Score like a per. Is this an averaging per player per something or score?
Return is just, it's not a cumulative. It's just it just means the score for one game, not a cumulative. I mean, for example, you win or lose just 0 and 1, and you.
Right, 0 or win. So is this the?
This is for each game has its own different score. For example, if we play Pound, it's just 21 to minus 1. This different games have different score settings. Like this one is -5 to 35. The score of the game.
So yeah, my point is at point 2 there, the game has not ended, right?
It means how. I mean, it means how many frames we have put into the network to train, and while the network is training, the performance becomes better and better.
So basically, the same system is not for games. Right?
Yeah.
So it's actually it's not means the game continue to the end.
Some games shorter, some games longer.
It just means data. How many data we have put into the network to train?
If the current game ends and it starts again,
yes,
from the start,
yes,
and all these frames are stored in this
right. Also, all these frames are stored there. So some
play multiple times.
Yeah. So some frames are from long game, some frames from short game.
Yes.
Okay.
For one kind of.
Okay. Now still I'm not understanding.
Yeah. What's the point?
Yeah. What does it mean? The point about let's
put,
one point on the on the curve.
One. It is already 1.8.
Yes.
It means just for a certain amount of data we put into the network to train, we use a epoch or several epochs of games to evaluate the current return, to evaluate the current behavior, current performance.
Right now. The
evaluation.
If I use 20% data, let's say, okay, let's say maybe 20% data, then I can play. I'm not going to add any more data there. Just use 20% data, do the base training you can have. And that's what you have, for each method. That's allow only that amount of data. And you do the best you can, and then you look at the score for that one.
Yeah.
Is that interpretation?
Yeah.
Okay, and so that each figure is similar.
Yeah.
Okay. I'm not sure that's part of it's my understanding correct now. Okay, so you please confirm it. Because these figures are very confusing, right? Something that you don't really tell me exactly what they are.
I think it's you could just understand it. It's just the same with the deep neural network training, just the same as the classification tasks. Just how many. I mean, deep neural network training. It means how many data. The x-axis is how many data we put into the network, and the y-axis is the performance. This means
performance. Performance need another evaluate.
Yeah, evaluate.
Right, evaluate. You need many multiple trial, multiple games.
Or we can use the previous returns. Just like choose the previous to.
Okay. So what's the okay now the final return.
This one is about the stability. Stability. This is about the return. Return how the return changes according to different hyperparameters combination. The x-axis is just 24 different settings of hyperparameters, and
Perhaps it's optimized. 24 will be chosen hyperparameters.
And I'm not sure if, but the first one, the best one, is optimized. But this one, I don't think it is optimized. Just
the first one is one parameter, or is this the
one parameter, five
or one
parameter.
combination parameter,
Yeah,
one parameter.
one combination of hyperparameters.
Oh, there's the same thing. Suppose there's one set parameter has 10 parameters.
Okay, so this is all combining one.
This is combination 1.
Yeah.
The last one, the combination 24.
Yeah.
Okay.
Okay, so this is 24 different combinations of hyperparameters.
Yes.
And the y-axis is the final return, means when it trends to the end, the final return.
Okay, the 10 after about the 10 to the 9. Okay, that many data. So this means that, okay, this figure illustrated high parameter methods, right?
Yeah.
Okay.
So still the blue line is their algorithm, and the red line is the A3C. And we can see from the picture that their algorithm.
Which one is A3C?
The red one.
A3C, and what's the one that's called?
The blue one.
Blue one.
Yeah.
What's that? The very large one above that. What's that?
That's another very. Wait a minute.
Using different methods.
Yeah, different number of workers. Different workers and actors.
Okay. So I still think that who's scheduled to speak next?
Next week is for Linda, right?
But I suggest that she continue another session.
Maybe after
what?
the day.
What?
So what do you want to talk about? What some things
Not multitask. Multitask. She have not talked about. And there are also a few questions that we asked today. I hope you can clarify that.
Mm-hmm.
So you have something to next week?
Yeah, I might not be here next week.
What about the week after?
Mm-hmm.
What's your schedule?
I think I could talk after the already scheduled person. I mean the next and the 3 weeks after.
3 weeks? Wow, that's something. 3 weeks you seem likely. You're going back to Beijing?
Yes.
Okay. Yeah, you got it. You can. No. I think it's online. It's much easier because she pointed something that's nice. I think I don't like it. Okay. Good. I think today's presentation outcome is good job. I think I like this. So you present background, something.